All right, everyone, let's get started here. Good morning. So today we're going to be exploring the data set that we downloaded last time. And we're gonna really go through a whole bunch of functions that are gonna be very helpful for you when you get to the mini project, which is coming right after this. I think we'll probably get started on that on Wednesday. Okay, so if you recall, where we left off last time was we downloaded that data frame from the NASS or USDA NASS Quick Stats portal, right? So if you remember, that had a very weird, like a very long name, a whole bunch of numbers, didn't really make sense. So what I want to ask you to do is find the file on your computer and rename that to soybeans_NASS. And that is already a CSV file, so you can just leave as that. And then what we're going to do then is, I'm assuming that you all have already downloaded the GitHub repo again. And just something that perhaps I wasn't quite clear. So the GitHub repo is where we'll always be updating with new files and complete scripts and data and so on, and partial scripts as well. And so you kind of can think of that as like you're always downloading that to your computer every time that there's a new update, but you're never working off of that folder directly, right? So my goal is that you download that to your computer and then you move the files that you need into your personal folders, and that's what you work off of. So never really save your own things inside of the folder that you download from GitHub. That's kind of what I'm trying to say. All right. So what I'm gonna do here, and I really want you to follow along as well, because again, we're gonna be creating a new project. And if anything, that this is the first step for things to go well, right? So you have to have this done correctly to being able to import data and export anything else. So I want to ask you to go to your to the folder that you have for this course. I'm going to go on mine here. So let's see, mine would be at this level. Right, so this would be my main folder for the course. What I want to ask you to do is what you can do is every time that you download a new version from GitHub, you just copy and paste that here. You can totally overwrite the one that you already have in here, because again, you're not supposed to be saving your own files in that folder. It's just a way for you to get files I share with you. So I want to ask you to create this folder called 02NASS. And this folder should be at the same level as your main folder of the course. So once you create that, it should be right below your 0 on data wrangling. So we're going to do a new project, new files, starting kind of from scratch. And so that's what I wanted to create a new project. So once you create the 02NASS, you go inside of it, and then you create the data, code, and output folders. I already have it here on my side, but you'll have to create on your side. So again, we're just setting up the folder structure for a new project, and I really want for you to really understand this process, because it is simple and it's also easy to get lost and do things in a way that it wouldn't work, but at the same time is a very powerful mindset to really come in with your data and thinking about projects in that way. So once you create the data, code, and output folders, please go ahead and move that soybeans NASS data. So again, the one that we downloaded from GitHub, move that into the data folder. I already have it here. So this is how it should look for you. And again, this is that data set that we got from NASS last class, that it had a weird name. So we first renamed it, moved to here, and I'm just going to open it so you see it's that like really, really messy data with like 6,300 rows. So that's the one we're talking about. We're not talking about the field soybeans example that we did on the data wrangling. That's not it. Once you do that, make sure then you go into the code folder and then copy here or move here from the GitHub repo that you downloaded that is on the, let me come here on my side. So on the GitHub that you downloaded on 04 class code, you have the 030 NASS summary partial.qmd. So that's the file you want to copy or move now to the 02 NASS code folder. All right. So, oh, sorry. Did someone have a question?
Yeah, you grabbed it from the class code over there.
Right, yeah, so, yeah, let me show that again. So, if you downloaded the latest version after I sent the email last night from GitHub, it should be on that folder that was on the 04 class code, and that would be the 030 NASS summary partial QMD. So we want to move that into the code folder inside of your 02 NASS. All right, so does anyone online have a question?
Yeah, can you repeat the first one, where to move that file, the soybean one?
Hold on, I think maybe we got a couple people that are unmuted. Let me see, try again, Umar, I couldn't quite hear it.
So could you repeat where to move that soybean folder? That first file, that we downloaded in the last lecture?
Yeah, so the file that we got from NASS, right? So that one, I mean, I didn't share that with you because we downloaded it individually. So we would, if you don't have that, then I guess, you know, you should probably watch the previous lecture and go through that. But that's what we downloaded from NASS, which we just downloaded, I guess, you know, for me, it was on my downloads folder. I don't know where that would be in your computer. But it was a very weird name file, right? So with a whole bunch of numbers. So we just renamed that to soybeans NASS and then moved that into the data folder. Does that help?
Yeah, got it.
Okay, perfect. All right, so, you know, again, I'm just gonna quickly go through this one more time. So we created the 02 NASS folder at the main folder of the course. We went inside of it, created the data, code, and output folders. We went into the data folder and brought here the soybeans underscore NASS, which we downloaded last time. And then we, from the GitHub repo, you know, if you downloaded that after I sent the email, you should have the most up-to-date version, which inside of the class code folder, we have the 030 NASS summary partial QMD, which is a script file. We move that into the 02 NASS code folder, so we can use that to code today.
Dr. Bastos.
Yes.
Why do you have two files in your code folder right there?
So in my case, I also had the complete version, which you all don't, at least not yet.
All right, make it.
Yep.
Thank you.
Yeah, absolutely. Okay, so assuming that everyone was able to get the data inside the data folder, the code inside the code folder, let's create an RStudio project, right? So you basically just launch any RStudio window. It could be from a previous project. So I have already created on my side, but I just want to walk you through again the process. So for you, even if it shows preview none, or maybe shows the 0 data wrangling one, whatever it is, you just click on that blue button on the right. You say new project. You click on existing directory. We browse to that 02 NASS folder that we just created. So that would be, again, at the main folder of the course. You should have a 02 NASS. So you go inside of that. You should already be seeing the code data and output folders that we just created. And then here, click open and then create project. I'm not going to create myself because I have already done that, but you should go ahead and create a project yourself. And that would launch a new RStudio window. Again, focus on this project. Okay. So again, what we just did now, it's something that we're going to be doing a lot of times this course. Is something that I really encourage you to get the habit of if you keep using R, because it's really going to set you up for success when you're creating your projects and the data folder, the folder structure that goes with it as well. Okay, so how do you know that you did everything successfully, right? So you should see the 02 NASS name on the top right saying that you are in the right project. If you see preview none, or if you see something else, it didn't work, then you have to troubleshoot and see what happened, but it should be seeing 02 NASS. With that, if you come on the Files tab here, we click on that blue button to go to the main folder of this project, and we click on the code folder. And please go ahead and click on that partial script. You should only have that one at this point, and that would launch the partial script for us. I'm just going to come all the way to the back. Again, if you're not seeing the outline, you can just toggle that outline on and off. We're not really going to need the outline, but just so you see what we're doing. And, you know, I don't want to spend too much time telling you about the different script type, but we are using a different script type today. It's called Quarto. It's a .qmd extension, so it's not the R Markdown anymore. It is very, very similar to R Markdown. So everything that we talked about as far as having the chunks, having, you know, the headings, different levels of headings, and doing comments outside of the chunks, all that applies. Quarto is just a newer version of R Markdown, but I didn't want to introduce that to you first thing, so at least you know the projection of how things evolved. But really, we're going to be using Quarto from now on. And Quarto is also a somewhat newer thing. It's probably, I think, was launched by our studio last year, like mid-year, around June. And so, you know, I really hope that you all downloaded, when you were preparing for the course, that you downloaded the newest R Studio software, because that Quarto comes with it. So you should already have Quarto installed if you did that. Okay, so today our goal is going to be to explore the soybeans data set using tables and plots and really understand what's going on and ask this data set some questions and get answers back. And again, this is a soybeans production in bushels at the county level for Georgia across, I don't know, 60 years or something like that. So it's a really cool data set to play with. So if we just come here on the first chunk, I have commented off the install packages dlookur. You can just like uncomment it, run just that part of it and install it. It should be pretty straightforward. But once you do like run that and install this package, which you don't have yet, then you can just go back again and comment it off, since, you know, we only install packages once and then we load them every time. So once you have that installed, you can just go ahead and play this chunk to load all these different packages that we're going to be using today. And if you were able to install dlookur successfully, it should load it successfully as well. There are some messages that appear down here, which is mostly coming from the tidyverse package. And I basically just ignore. Yeah, someone had a question.
Yes, sir. When I went to run that, it said error in library, tidyverse. There is no package called tidyverse.
Okay, so if you don't have tidyverse yet, I think tidyverse was one of the packages on the first class that we installed. I mean, if you don't have it, just feel free to go ahead and install it, right? So we would just basically do the install.packages, open and close parentheses or quotation marks, and then do tidyverse, and then just install it. I think, does anyone having issues with tidyverse?
I think that worked. Oh, it muted. No, we're unmuted.
When I ran it, I got a bunch of methods overwritten by dplyr.
Yeah, so if it normally gives a lot of messages, it's just like telling you some of the things that are in conflict. But if it's just even if it's just a warning or a message, you can ignore. It's really, you know, what we want to avoid is if you don't have tidyverse altogether, because then that's going to be bad. And I thought I had included in the first class getting ready, but maybe I didn't. I have to check on that. Did you have a question?
No, I was just saying that the same message came. Yes.
Okay, yeah, so that one we're installing up here, right? So that one already left the D looker. Already left there, so we can just install that and then comment off. Was everyone else able to, after installing dlooker, and if you needed tidyverse, was everyone able to load all packages here? Okay, so I'm assuming everyone was able to. If you were not, let me know. So tidyverse is basically just it is a package that combines a whole bunch of other packages that work together. So dplyr, tidyr, ggplot2, and many others that are within using the same philosophy behind them are all part of the tidyverse. So they just made this compilation of packages to make it easier to load all of them, because we normally use all of them together for data wrangling and plotting. Yeah, so just to make that clear. Okay, so assuming everyone was able to do that, let's now import the data. So something to notice here, every time we're importing something, especially if it's a data frame or a data set, we're going to use a function called read underscore something, right? So if you recall, last time it was an Excel file, we used the read underscore Excel. Now it is a CSV file, so we use the read underscore CSV. If you were able to create the project properly, have the folder structure properly set up, and have the files in the right folders, you should be able to come here and say .. to go a level up, so we get outside of the code folder. And if you hit tab, you should be at the main project folder. You go inside data and you hit tab again. It should populate already with soybeans underscore NASS. So this should work by default if you did properly the folder structure and the project setup. So if we run it, it imports it, it just gives us some messages, but just if you want to make sure, for some reason my environment is not appearing, but so if, if I just come here and say soy, it should print that data frame for me. So I know that the object is here, is within my environment. For some reason, my environment is not appearing, so I cannot really show you soy appearing up there, but for you, it should be there. So this is really the first step, right? Is bringing this data set into R and just exploring it a little bit. So we had some introduction here saying what was the goal. We did some setup where we load all packages that we need for this R session and also import data. And now we're going to do some EDA. So EDA stands for exploratory data analysis. Is always something that I encourage you to do, regardless of the data set you're working with. So the first thing that I want to do is just print soy and just take a look at what it is. Okay, so first thing to notice here is we have like almost 6,400 rows here. So 6,400 rows here, a very large data set, and 21 columns, right? So if we just quickly take a look at the columns here, we have something called program, and then year, period, week ending, geo level, state ANSI, which is just a code, ag district code, county name, county code, ANSI, zip code, region, watershed code, watershed, commodity, so soybeans, data item, which says what we did, so production measured in bushels, domain, which just says total, domain category, value, and CV. So we can see that there's a lot of things here that we probably don't even care about, right? So one of the things that we're going to do is when we're wrangling this data, and again, remember, data wrangling is always a part of data analysis, regardless of which data you have. So we're going to do some data wrangling here. Now, I just want to go ahead and ask for a summary. So if you just go on to the next chunk, I'm just asking for a summary of it. I'm not asking you to code yet, but just go ahead and run that. So really interesting. We see that, so year is seen as, a lot of stuff is seen as character, and that's why it gives us just like a length and says character. It doesn't give this statistical summary. But for example, something that should be seen as numerical is the value, which is the actual production value in bushels. And R actually is interpreting that as a character. So that is something we're going to have to address when we're doing data wrangling, is to make sure that this column is seen as a number and not as a word, right? Okay, so if you come, so again, this data set has like 6,400 rows. That's a lot of rows for you to just browse, right? So if we do a view here, like we were doing the first time, it's not going to be super useful because, 6,000 rows is going to be a lot of scrolling and it's going to be hard to keep track of what's going on. So one of the things I want to show you here is a new function that is coming from the dlooker package. Is if you just come here on this chunk and you use the pipe and you say diagnose. So this function here is coming from the dlooker package. And so it creates a table for us with 21 rows. I want to view this. You don't have to view if you don't want to, but I just want to add this so it's easier for us to see what's going on. So if we come closer here, it has this column called variables, which it has one for each one of the columns in the original soy data set. It says what is the type of that variable. So we see year is numeric, but then, for example, value that should be numeric is actually character. It gives us some information of the missing count. So how many NAs we have in those columns. So for example, week ending has the same number of NAs as number of rows, meaning that the entire column is NA, which is really not a useful column for us if you think of that, because, how are you going to use that if it's just all NAs? And then something also interesting is see the unique count. So what does this mean? It is telling us how many different values there are within each one of those columns. So for example, if we come under county, it says we have 157 different values across all those 6,400 rows. So this kind of makes sense because Georgia has, I don't know how many counties we have. Anyone knows, remembers? 155, something like that. So it's pretty close. I wouldn't expect to have all counties here because not all counties produce soybeans, but it's it makes sense to have 157 unique values under the county column. But something that I just want to show you that caught my attention here is that program has two different unique values. And I just want to explore that a little bit and see why that is. So I want to close this tab here and just keep going. I'm going to delete the view here because that was just for us to make it easier to see. So if you come here on the next chunk, what we can do here is use a pipe and type distinct. So there is a column function called distinct, and you give it a column name. So I want to give it program, and it's basically going to tell us what are those distinct values for us to understand. Okay, so there is the two different values inside of this column are census and survey. And this was a question I think Arminder had the last time when we were creating the selections on quick stats, was if we should select program. We did not make a selection there because I wanted you to come across this issue, but we could have selected either survey or census at that point. Okay, so if you, what I want to know now is, okay, so we have census and survey, and the thing is for a given, so we have a lot, oh yeah.
I just had a quick question.
Yeah.
I typed in program with a lowercase p and it came up error, but then I did it with an uppercase p and it showed up. So does it have to be uppercase anytime?
Yes, well, the thing is R is case sensitive, right?
Okay.
So if the data frame is uppercase, you have to follow that. And if we just print again soy, just so we take a look at it, program at this point at least is uppercase. But it will change in a second because we're going to use the clean names function to standardize that. But right now, since we haven't yet, then yeah. Yeah, absolutely. Okay, so the thing is, what happens in the US is almost every year there's a survey, and then every, I don't know, 5 or so years, there is a census. Meaning that if we use the census data, there's going to be a lot less data for us to work with. So I really want to use the survey data. However, it is interesting because let's say that for 5, if you think of 5 years, from year 1 to 4, there's only survey data, but then year 5, there's census and survey, meaning that for a given year, you're going to have 2 pieces of information that are pretty similar. So I want to avoid that here, and I just want to see, if I want to understand which one we should keep. I'm telling you that it's survey, but if for some reason this wasn't intuitive, how would you check that? So if you can just comment off the distinct right there, because distinct only told us which were the two different levels. We don't know which one of them have the most data at this point. So I want to ask you to do a group by and say program uppercase P inside the group by. And as you know, group by itself doesn't do anything. So let's add a pipe at the end of that. And I want to introduce a new function to you that's called tally. So tally is pretty much going to count for us how many observations there is within census and within survey. So if you run that, we see that there is a lot more data that is coming from a survey than there is coming from a census. And at this point, since we want to keep the most data, let's just, when we do the wrangling in a second here, we're going to basically filter to only have data that is survey based. All right.
Dr. Bastos, I got an error in group program, object program not found. You know what it is.
Did you make sure that you have the pipe?
Capitalization, I think. Nope, still didn't work.
Oh, you don't forget to put the hashtag in front of this thing.
1 second.
You have to comment off the distinct first.
Yeah, thank you.
All right. Perfect. All right, so now let's do some wrangling here. It's going to be mostly this much wrangling we're going to do for this data set, and we're going to have some different issues on the wrangling. And this is something that I also want you to notice is that each data set is different. There is no recipe for wrangling. You always have to be thinking of what you need, where you are, and kind of think through what steps you have to do to get there. So I left you there the soy. Someone has a question?
Yeah, I'm getting an error that I couldn't find the function tally.
Okay, so tally is coming from one of the packages within tidyverse. Were you able to load tidyverse?
Okay. No,
Yeah, so maybe that's why.
I installed the DLooker packages, but the tidyverse still wouldn't.
Yeah, so if
Okay, I need to install that too.
just
Gotcha.
go ahead and install that and then comment off and then run it. All right, I'm gonna keep going, but
Gotcha. Thanks.
let me know if you have issues. All right, so I left you here pretty much just using soy and clean names. So if you just run that at this point and you print soy W, it's just basically gonna have the headings all lowercase and standardized. So right now, then everything is lowercase. So now, if we use P uppercase, it's not gonna work at this point at least. Okay, so as we talked about, there is like 21 columns and a lot of them we really don't care about, right? So what I want to do the first thing is just to select the columns that we need just to help us visualize, at least on the column size, what we have and what we can do with them. So add a pipe at the end of clean names. Go after that comment of the keeping only survey data. And then let's use the function, sorry. So here we're keeping the survey data, so we're not doing the selecting yet. So to keep only the survey data, this is a function that we have already used. It's going to be the filter, right? So we say filter. Remember that now program is lowercase because we just use clean names. So we say program equals, and then open and close quotation marks, and we say survey. Survey is all uppercase because that's how it's in the data set, right? So that's how it came from NASS. So if you just have your cursor anywhere here and you run it, it should have worked. And if you just print soy W below, it's going to have less than 6,400 rows, right? It's going to be less than that because now we're only keeping the survey data. Okay. So now after this, I want to add another pipe. Come below the selecting desired variables comment and use the function select, right? So if you recall for select, I always encourage you to call specifically what package we want it from. That's dplyr, : and then we say select. So I want to keep here the year column, the county column, and the value column. And I'm going to run this now, and I just want to show you what's the output, which we should kind of expect already. So year, county, and value. However, I want to rename this column here called value because it's not very intuitive of what it is. So this value column here is really representing production in bushels, right? So right here, I come back to the select. I can just type prod underscore BU for bushels equal value, because then select here is going to do two things. It's going to select the column value, but also rename it to prod underscore BU for bushels. So if we just run that and print below, so we see what happened, that's exactly what we have, right? So we have the year, county, and now we have a column called prod underscore bushels. Okay. No, I'm seeing here, so before, and maybe that changed for some reason, but before I was seeing, oh, I think let me just do something very quickly. You don't have to do it, but I just want to show you. So I want to arrange the soy W by year and see something here. Okay, well, never mind. I had another step here that I had to do last night when I was going through this. But I guess maybe we don't have anymore, which was this one. So let's just keep that. So one of the reasons why production in bushels is being interpreted as a character by R is because it has this comma here. So R doesn't really add comma to separate the thousands when it has a numerical column. And because the original column came in with the commas, that's why R interpreted as character. Now, for us to transform this column into numeric, first we have to remove this comma here. So you can come below the removing comma from prod view comment. And then we're gonna use a mutate. So we're gonna just overwrite on top of the same column. So that's gonna be prod underscore view. So that's the name of the new column, which is basically just overwriting the old one. And then there is a function from the string R package, which is part of the tidyverse, that is str for string underscore remove. Again, this function is coming from a package that is part of the tidyverse. So if you had issues with the tidyverse, it may not be available for you, but that's where you would find it. So the first thing that we say here is what column that we want to look for a certain pattern to be removed. So again, the column is the same, prod underscore view. We add a comma, and now we tell what is the pattern that we want to remove. So it's basically, we say within quotation marks, comma. Right, so make sure that you close your parentheses. So we should have a one parentheses closing the string remove function and then one closing the mutate function. Oh, and I actually forgot to add a pipe after the select. So make sure that you also do that. So we have this pipe here to connect with the next function. So if we go ahead and run that, and now print soy W, well, it actually didn't work for some reason. Let me see, that's funny. Huh. That is quite interesting, because it seemed like it removed for some, but for the other counties didn't. That is kind of odd and didn't happen last time, so new. Interesting. Well, I guess let's keep it for now and try the next step, which is transforming from character to numeric, and see if that works. Because maybe, yeah, I'm not sure why that's doing that. But let's just try to move on and see if that gets fixed on the next step. So on my side last night, at least all the commas were removed. So let's just assume that that's the case here. Not sure why that's not doing the same, but the next thing now is to transform from character to numeric. So we add a pipe to connect. We come here and we use another mutate. I'm again going to override that column prod view. And there is a function called as.numeric. I want to use that and then give the prod view inside of it again. So we can just go ahead and run that and see if that works. Okay, I mean, it works now because production in bushels is now a double, so that's numeric, is not anymore what it was before. And yeah, I mean, it basically removed the data from other counties, which is kind of interesting. I wasn't really expecting for that to happen. But we'll see. Yeah, again, this didn't happen last night, but you know, it's one of the beauties of programming is that sometimes things don't work as you planned. Okay, so last thing then is, so production in bushels, you know, sometimes we're gonna get some pretty large numbers here, and I just want to avoid that. So I want to transform that to million bushels instead. So we just add another pipe at the end here. Go below the comment saying transforming production from bushels to million bushels. And let's use a mutate. Now we're gonna create a new column called prod underscore MIBU for million bushels, which is basically just gonna be production underscore bushels divided by a million. So that's 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6. And then if we run that and print it, we should have a column now that mostly ranges from 0.00 something all the way to 1 is the maximum on a county level observed for this period. Okay, I just want to leave it up here for a moment just so y'all can see. Yes.
What says object product being on county, because I do the same way you do.
Oh, you didn't see the.
All right, so if you got all of your parentheses right, if you got all of your pipes right, then we should be good. Was everyone able to get to this point? Did you get your production million bushels as a double when you printed? Okay, I'm seeing some heads nodding yes. If there's any issues with anyone online, let me know. Please feel free to jump in. Okay, so I'm gonna keep going here. So the first thing I want to do is just plot the distribution of this data so we understand how does production on a county basis for the last 6 years looks like. Yes. Yep. Hmm? What? Were you able to catch up? Okay. All right, so you know, now that we basically did the wrangling of this data set, let's explore it a little bit. So if you come here, we're gonna do a second round of exploratory data analysis, but now using some more plots and tables. So first thing I want to do here is just explore the distribution of production in million bushels at the county level for the last 60 years. So I left you some code here. If you just run that, you know that you're just gonna get an empty canvas with the variables that we are saying that we want, but no data yet because we have not added any geomes. So if you just add a plus, so remember within ggplot, we combine things with plus. When we're doing data wrangling, we combine things using pipe. So just to not get those confused. So we're gonna come here and add a geom underscore density. It's gonna make a density plot for us of the distribution of county level production in million bushels per acre. So we see that here, you know, it is pretty much a skewed distribution. We see that most of the counties were producing, you know, maybe like 0. I don't know, 0.02 perhaps million bushels in a given year, which is not a lot, but we had this long tail here showing that at least one county produced near to 1 million bushels of soybeans in a given year, which is pretty cool. So this just to give us an idea of the distribution of this data. And if you're not familiar with density plots, this is pretty much like a histogram, but instead of having the histogram bars, it just basically outlines the shape of those histogram bars with a line. I think it's more it's a more straightforward way to think of it, I guess. So if you were a normal distribution, you know, you would have the bell shape type of distribution here. That's kind of what is doing for us. It's just showing the frequency or density of this of observations of production. Okay. So the next thing I want to do here is to plot production distribution by year. So let's just start a ggplot here. Didn't leave you anything there, so let's start there. If you remember, always the first argument is the data set coming in. So we want to use soy_w, which is the wrangled version, so not the raw data anymore. Then we use the AES function to determine the aesthetics of the plots. So we say x equals, I want to say year, so I want to have year on the x-axis, comma y. I want to have production, so prod underscore million bushels. That's what I want to have on the y. And then I want to just tell you from now to just add a comma and there's an argument called group. I just want to say group equals year. And then I come at the end of that ggplot call, add a plus, hit return, and let's add a box plot. So geom boxplot. So Boxplot is a way for us to see the distribution that's going to just help us to understand how this was varying. So if you run it and things work nicely, you know, we have these long box plots for each one of the years, which if you look at the horizontal black line, that would be the median of the production. And this is for a county level. So we see how things were not producing much, and then they went up, and then they kind of came down and went up again. But we have a lot of outliers, right? Meaning that even if the median here was like 0.1, we still had, you know, if we take, for example, like, I don't know, this, let's take 1980. So 1980, the median was probably near 0.12 or so. But on that year, we also had counties that produced almost 800 or 0.8 million bushels, right? So there's just a long distribution. Yes.
Why error and they're not talking about ggplot? You know what I'm talking about?
Yeah, so ggplot, it comes from the package ggplot2, and ggplot2 is part of the tidyverse. So if you were able to load the tidyverse on top, then it should work. If it's not, if you don't want to, so you will have to install tidyverse later, but for now you can just do a library like right here on this chunk ggplot2, and that should fix it. All right, so again, we see there is a large variability within a year, but also over time for the production of soybeans in Georgia at the county level, which is kind of expected. But you know, just a large variability. Kind of interesting to see that using a box plot. Say that again. You mean one on the y-axis?
So you asked me, we remove 92 rows.
Oh, yeah, gotcha. Okay, so this is just a warning here. When ggplot says that, it's probably because there were some years where there were no data. So we basically removed that that empty year from the visualization. Yes. So Sundash was asking about the remove 92 rows. It's just because there was no data for some years possibly, and so we just removed them from the visualization. Okay, so we're starting to explore this data set here, trying to understand what's the distribution of production. I always encourage you to do something like that when you're working with data, especially if it's not your data. So we don't really know what's going on behind the scenes. Okay, so what if now I wanted to have a similar plot? So now you can think of it that within each one of the box plots above, each box plot contains all counties reported for that year. What if now I wanted to have a plot where each county would be a line over time? How do we do that to visualize on a county basis? So come to the next chunk. And what we're going to do here is, so I left you some code already. So we have, again, year on X, production on million bushels on Y, and then I want to add a color by county. So each county is going to receive a different color on this coming plot. We add a plus at the end there of those parentheses, and we're going to add a geom underscore line. And let's just run at this stage so you see what happens. It may take a moment here, but it looks terrible because we have like 157 counties, meaning that we have 157 legend entries, which makes it just very difficult to visualize. So one way to get around that is if you come back to geom_line, it has an argument called show.legend that is by default true. We want to turn that to false. So, even though we're not going to know which line is which county, but at least we can see the data, right? So going back to geom_line, saying show legend equals false. So this is what it looks like. And again, each line is a different county. And because we have lots of counties, it's not also very useful of a plot. Imagine if you only have 2 or 3 or 5 counties, then you could really follow which ones are up and down and, how they're behaving over time. So this is kind of useful to see that there's a lot of variability as well, but it's not a very good map because there's just so much going on. Okay, so maybe, we visualize mostly with plots. Now let's create some tables here. So let's say if I want to know what was the highest production record of any county in any year in this data set. If somebody came to you ask, what was the highest soybean production ever in Georgia and where did it happen? This is what we're going to answer here. So to do this, we're going to start with soy_W, which is our wrangle data, use the pipe, and we're going to basically do a filter. And I want to show you a cool trick here to do with this type of question. So I basically want to filter the column production in million bushels, but only the cells that are equal to the maximum value of that column. So how do we say that? So basically say it again?
Just by maximum?
Yeah, I mean, that's part of it. So we say equals, and then we say max, and max is a function, right? So we have to open and close parentheses, say prod_million bushels. If we do this at this point, you can just go ahead and run and see what happens. We get 0 rows. And maybe I didn't make enough of a point when we got there, but the reason why it's giving 0 rows here is because this column production million bushels has an NASS. And just like the mean function that we did on the data wrangling exercise, the max function, if you have an A in the column that you're asking for that, it's going to return you nothing. So if you recall on the data wrangling exercise, there is an argument called NA remove or NARM. We set it to true. So it first removes NAs and then gives you the maximum. That's what we have to do here. So if you run it, you should get back this result that the county that produced the most soybeans was Sumter County in 1984, and it produced almost 1 million bushels of soybeans. Right, so imagine that we had a data frame with 6,400 rows. Now we're just trying to learn from it instead of like doing manually. We're just using functions to get us there. Okay, so what if we want to do the same, but with the lowest? So one thing that we can do is just copy and paste what we did here on the chunk above, just paste that here. And then, the only thing we have to change is that instead of doing the maximum, we're actually extracting the minimum. So if we do that and we run it, So this is kind of interesting and something I want to call your attention to as far as NASS data. So what happens with NASS reported data is that, you know, the main counties that do something that you're querying. So in this case, the main counties that produce soybeans have their own entry on that county column. However, all other columns that produce a little bit of soybeans, but not enough to make it into their own row, they get all lumped together into a category that's called other counties, which is kind of interesting to learn that combining some other counties, we don't even know which ones, produce that little, like 200 bushels of soybeans in a given year. But we really don't know what counties those are. So it's not very useful. For this to be useful, we have to do a little tweak here where right after soybean pipe, we want to do first another filter, which is remove this other combined counties values first, then only leaves the counties that actually reported, and then we do the minimum. So to do that, you probably are already thinking we're going to do a filter, and then we're going to say the column that we want to filter, part of it is called county, right? So county. So up until now we did equal, right? But now we want everything except that. So to do that, we, instead of say equal, we do exclamation point equal, which is the way that we programmed to say that we want different than, right? So we want all counties except or those different than, then open and close quotation marks and copy and paste this. Don't forget to add your pipe at the end. And then just run it. So this first is filtering out all the entries that are other counties and then getting the minimum production. So the minimum in Georgia was County Glasscock in 1959 that produced about 500 bushels of soybeans in that year. Okay. So we are already at the hour. I don't want to keep you for too much longer, but we're going to stop here today. We're going to finish this script next Wednesday on the first hour. We're going to start another script and also finish that hopefully within the first hour. And then the second hour, I'm going to introduce the mini project, which is basically going to be, I'm going to be asking you a whole bunch of things that we did through today's exercise, but with a different data set. It's going to be a different crop. Perhaps it's not going to be production, perhaps going to be yield or planted area or something like that, that you're going to all have different types of projects individually. So we're stopping here today, but next class we'll continue and finish this and then potentially begin the mini projects as well.